It was important to start this module by talking about how to document data quality in that last lesson, and that sets us to jump into this next lesson, how you actually collect drainage water samples. I want to start with one very common term in our field is the term hydrograph. A storm hydrograph is a graph that illustrates how flow rates change over time during a storm. The concept of a hydrograph essentially is the graph of the hydrology and helps us understand the difference between base flow and storm flow, which matter for monitoring. Storm flow is precipitation that reaches the channel or outflow point quickly, whereas base flow takes a longer time to get to the stream or outlet and flows more consistently. This illustration shows storm and base flows for a stream, but we have these same concepts for tile drainage. Most tile drain fields will have consistent periods of base flow, where the water table is just being lowered to the level of the tile and the flow rates are relatively consistent. But when you have a storm or rainfall event, you see a peak in tile drainage flow rates, depending on how dry the soil was previously, and that is a storm flow. Why does base flow versus storm flow matter for water sampling? Sampling during storm events is much more difficult than sampling base flow. It's hard to exactly predict when storms will occur, and they like to occur outside of traditional work hours. It can also be dangerous to be out in storms. As a result, we often use automated water sampling equipment so that personnel are not forced to be out under those adverse conditions. We'll talk about auto samplers in a minute, but I want to start by discussing manual grab sampling because this is the tried and true basic method of water sampling. You can't always afford an auto sampler for every project, and a farmer or landowner, for example, would probably just manually sample like this if they wanted to do edge of field monitoring. So this type of sampling is very valid, even for today's very high-tech world. How do we actually do this in the field at our sites? First of all, you bring your sample collection stick, which doesn't have to be fancy, just a clean bottle securely fixed to a stick that's long enough and sturdy enough to access your water without breaking. Position the sampling stick to collect water flowing over the stop log, or if you're sampling from a tile outlet, collect the water from the outlet, but you don't quite take the sample just yet. First, you need to rinse the bottle 3 times with that water to make sure the water that you have collected in the bottle eventually is truly representative of the water that you want to sample. Dump the rinse water outside of the control structure or away from the outlet. Fill the bottle and cap it. Affix the label if it's not pre-labeled, and for our samples, it's all right to have some head space, that is air space, at the top of the container. Now that's manual grab sampling. Let's go back to the topic of auto samplers. There's a lot of information for you to peruse if you're interested in this table in the pros and cons of sampling approaches. To me, the major advantage of using auto samplers is that we can collect samples under a variety of conditions, all in a consistent way across a number of sites, and simply not have to be there. That's the biggest benefit. Automated samplers, however, are expensive to purchase and expensive to maintain. And anyone who has ever used an auto sampler knows they are far from trouble-free. Let's talk about what goes inside an automated sampler. And note the pictures that I'm showing here are the Teledyne ISCO auto samplers that we've always used in my lab, but there are a number of different brands. Every auto sampler has electronics to run its operation and memory. And then there's a small pump that kicks on when it's programmed to kick on, and that's what pulls the sample up into the bottles. Those first 2 components are housed at the top of the auto sampler. In terms of bottle configuration, you can have 1 large bottle if you're doing a large composite sample. We'll talk about what that means in the next lesson. You can have up to 24 plastic bottles, up to 24 glass bottles, which I sometimes prefer if we acidify in the field. Or you can use shells that contain disposable plastic water sample baggies. We've recently started to use these because it greatly reduced bottle washing, which prevented a lab mutiny, I will say. Just kidding about the mutiny. But again, you can see how personnel, even lab personnel, plays into monitoring system design. Finally, more expensive auto samplers like the 6712 model have stage or depth recorders that connect to them. We'll talk more about this in the next lesson when we discuss flow-based sampling. I'll also say that there are multiple flavors for auto samplers. For example, you can buy refrigerated ones depending on your needs and your budget. I want to take one quick sidestep from grab sampling or auto sampling to show you real-time nutrient sensors. This technology is really the next frontier, very exciting for the field of water quality, because we now have the capability to have near continuous nitrate concentrations basically in real time. So issues like how often should I sample become moot. Real-time nitrate sensors don't actually involve sample collection and sample analysis. Rather, they use technology like in situ ultraviolet spectroscopy to generate nitrate concentrations in real time. The downside of these sensors, obviously, is their capital cost. Each sensor, plus all the associated parts and pieces for logging and streaming to the internet and data plans, etc., are on the order of $10,000, $20,000, even up to $40,000 a piece. Here I'm showing one tidbit from our experience with these real-time nitrate sensors. We deployed a nitrate sensor at the inlet of a bioreactor where we also had an autosampler collecting a discrete sample every day at noon. You can see that the sensor often did not match the samples that we analyzed in the lab, but it was those lab analyzed samples where we perform rigorous quality control that we'll talk about in a later lesson. It's those lab analyzed samples that I consider to be the truth for what was happening with the actual nitrate concentrations in this water. We still need to figure out if there was something else going on here in our experimental setup, but I show you these data because this is a cautionary tale that just because you have an expensive sensor doesn't mean you can set it and forget it. Sensors are dumb. You are smart. It is our responsibility as scientists, and will always be our responsibility as scientists, to make sure our data meet proper checks and standards. I'm also showing some YSI handheld sondes here. A challenge with these that we found is that they need to be calibrated every couple hours. Hence, they're not really field deployable on a permanent basis for continuous water or continuous nitrate or continuous water chemistry sensing. These are good for spot checks as long as you've calibrated them right beforehand. See you next time.